Light is amazing. It acts like both a wave and a particle. This is called wave-particle duality. Think of the ocean. It has waves, right? Light is similar. It travels in waves of energy. We can see this when light bends around corners. But light is also like a stream of tiny particles called photons. Imagine a garden hose spraying water. The water comes out in individual drops, right? Photons are like those drops, each carrying a bit of energy. This duality is what makes light so unique. It's both a wave and a stream of particles. This might seem weird, but it's how light behaves. Scientists have done tons of experiments to prove this. It's a fundamental part of how we understand the universe. Have you ever wondered how light from distant stars reaches us? Here on Earth, sound needs air to travel, but in space there's mostly emptiness, a vacuum. So how does light travel through nothing? Light is a special kind of wave. It's an electromagnetic wave. This means it's made of vibrating electric and magnetic fields. These fields can travel through the vacuum of space without needing any stuff to move through. And get this, light travels incredibly fast. In fact, it's the fastest thing in the universe, zooming along at approximately 299,792,458 meters per second. That's like going around the Earth over 7 times in just 1 second. This incredible speed allows light from the sun to reach us in about 8 minutes. And light from distant stars and galaxies can travel for millions or even billions of years before finally reaching our telescopes. We all know gravity, right? It's the force that keeps us on the ground and makes things fall. But did you know that gravity can even affect light? It's true. Albert Einstein's theory of general relativity explains how massive objects like stars and galaxies actually warp the fabric of space-time around them. Imagine a bowling ball placed on a trampoline. The ball makes the trampoline sag, right? Gravity is kind of like that. It makes space-time sag around massive objects, and anything traveling through that warped space-time, including light, has to follow the curves. This bending of light is called gravitational lensing, and it can cause some pretty cool effects. For example, it can make distant galaxies appear brighter or even distorted, like they're being viewed through a giant magnifying glass in space. The universe is a vast and ever-expanding place. Imagine a loaf of raisin bread baking in the oven. As the bread rises, the raisins get farther apart. The universe is like that loaf of bread, and the galaxies are like the raisins. As the universe expands, the space between galaxies stretches, causing the light traveling through that space to also stretch. This stretching causes the light's wavelength to increase, shifting towards the red end of the spectrum. That's why it's called redshift. It's like when a car honks its horn as it moves away from you. The sound waves stretch, making the pitch lower. Redshift is super important for astronomers because it tells us how fast the universe is expanding and how far away distant objects are. By studying the redshift of light from distant galaxies, we can learn a lot about the history and evolution of our universe.